Let's take the derivative of cosine cubed of x. Wait, what does that mean? What does it mean when I take cosine to the third power? Is that cosine times cosine times cosine and then I multiply by x? No. Remember this notation. This just means you take cosine of x and then you're cubing that whole thing. It's just shorthand notation for cosine of x, that entire thing cubed. And once we write it that way, it's now clear how it's a composition. It's now clear what's the inside function and what's the outside function. Cosine of x, that's the inside function. That's the first thing that happens to x. That'll be our g of x. And then the last thing, the second thing that happens is the cubing. So in this case, the outside function is just going to be the cubing function. So the outside function, if we use the f of u notation, it would just be u cubed, like so. All right. Inside and outside. Let's apply the chain rule. And let's just try to do this all in one chain of equalities. All right. So first we have to take the derivative of the outside function. That's the power rule again, right? So it'll be bring the 3 down and then take u squared. The derivative of the outside function is 3u squared. Let me write that up here actually. F prime of u is 3u squared by the power rule. But what is u? U is going to be the inside function g of x. Cosine of x. The output of cosine is the u variable. So we'll be taking 3u squared where u is cosine of x. Alright, so 3u squared. Alright. That should have been in blue, according to my color scheme. Alright, so that's the outside function, its derivative evaluated at the inside function. And then I'm multiplying by the derivative of the inside function. What's the derivative of this inside function? It's just the derivative of cosine. That's minus sine of x. So again, what's this piece? That's our f prime evaluated at g of x. G of x just on its own, thinking of that as the variable u, as that thing that we're taking the derivative of f with respect to. And then we multiply by the derivative of the inside function. That's what the chain rule says to do. Alright, and at this point, there's really not much to do. We can bring the minus sign out front. Might as well do that. So we got minus 3. Oh, and cosine of x squared, we can go back to our more traditional notation, right? We can write that as cosine squared of x, and then we're being multiplied by sine of x. Notice that when I write cosine squared x, sine of x, it's implicit that we're multiplying those two functions. I could put parentheses around them to make it clear, but when I write cosine squared of x, it's only that next thing that we're plugging into cosine before we square it, and then sine of x is being multiplied. So that's the answer. And now this is a general pattern actually in this example. This is called the generalized power rule. We're seeing it in action here. It's the power rule combined with the quotient, the chain rule. Okay. So what do I mean here? Well, this f prime of g of x, another way to write that, let me write that over here actually, it was 3 times g of x squared, right? 3 times g of x squared. So it's sort of like just applying the power rule but leaving g of x alone. That's what this means. That's what that part of the chain rule means. So the generalized power rule is just the general pattern of doing that. All right, check it out. So if you take the derivative of some function g of x raised to the nth power, n was 3 in the example, then that derivative is always given by the chain rule by taking the n down. So again, I'll do color coding. Take the n down. Let's leave the inside alone for a second. It's going to be g of x. And then we subtract 1 from the exponent. That's the part that's the power rule. That's the ordinary power rule. But now on the inside, we're treating the whole function g of x as its own entity, as this variable u. It's the stopover in the two-step process, right? It's like when you're taking a flight and you got to have a layover. That's what that variable u is like. And then we're multiplying by the derivative of the inside. That's what we saw in this example. That's the generalized power rule. Derivative of g of x to the n is n times g of x to the n minus first power multiplied by g prime of x. And we saw it in action in this example. But we actually saw it in action earlier as well. Check it out. In the previous example, we were looking at the derivative of this whole mess. That inside function, g of x, it's being raised to the 4th power, right? That's g of x to the n, where n is 4. And what did we get using the chain rule? We got something that looks just like this, right? It's n times g of x to the n minus 1 multiplied by the derivative of g. So in terms of the generalized power rule, this part right here, that's like our n times g of x raised to the n minus first power. Again, n is 4 in that example, multiplied by this part. And what was that? That came from the derivative of g. So those two things multiplied together. So that was actually another example of this generalized power rule in action.
Can I get you anything to go with it, Sheriff?
Agent Cooper here might want to try a slice of that pie. A cherry pie?
Best in the Tri-Counties.
Now that we have the generalized power rule written in this general form, let's use it to compute some other derivatives. It really is just the chain rule. If you don't want to think of it as the generalized power rule, you don't have to. It really is just the chain rule in the particular case where the outside function is raising something to the nth power. So check it out. This function f of theta, that's exactly that sort of thing. The inside function, it's not a function of x this time, it's a function of theta. That's okay. It'll be the same process, but I'm thinking of that right there as the inside function g of theta. So this is g of theta raised to the 3rd power. Okay, so then the derivative of this function then will be, first apply the power rule around the entire outside, right? And then cosine theta plus sine theta, that's my g of theta on the inside, and then subtract 1 from the exponent. So that right there, that's like n times g of x to the n minus first power. We're not done. We need to remember to multiply by the derivative of the inside. So then we multiply by the derivative of the inside. That's, let's see, we're taking the derivative of g of theta with respect to theta, mind you. So the derivative of cosine is minus sine of theta plus the derivative of sine. That's cosine of theta. There you have it. This is again the generalized power rule. It looks like n times g of x to the n minus 1 times g prime of x, where g of x and g prime of x, well, they're not functions of x, they're functions of theta, and they were these two pieces. And let's leave the answer that way. We'll leave the answer in blue and purple. Though maybe, I don't know, maybe you should call this color teal. this blue? It's a blue-green, a teal. I don't know what you call it. But let's leave the answer that way. Nice work.
G'day everyone. Today we're going to make dark green. We've got yellow and blue. Excuse me while I have a drink. Am I the only one that drinks hot chocolate in the world? I don't drink coffee, so that's me, I'm strange. Anyway, so now we've got the yellow paint. I'm going to add 30 ml of yellow paint. For a sec, and we're just going to stir the paint and see what comes out. There you go, it's changed to really dark green.
Next example, let's take the derivative of j of t. T is the input variable, j is the name of the function, and the function is sine cubed of t squared minus 4t plus 1. There's a lot going on here. This is a complicated function. Remember, sine raised to the third power of something, that just means the sine function of that thing, in this case t squared minus 4t plus 1, and then we're cubing the sine function. So I'm writing square brackets to emphasize that it's that whole sine function that's being cubed, not the t squared minus 4t plus 1. That's the function j of t, and let's use the generalized power rule to compute this. Alright, it looks like something raised to the nth power, and so I'm going to treat this whole thing as the inside function. Alright, so that'll be like my g of x in the generalized power rule, but here it's a function of t, so that'll be like g of t in the generalized power rule. Remember, that's just the quotient rule. It's a particular case. The quotient rule, what does it say in this case? Here we go. Let's compute the derivative of j. We bring the 3 down. We work from the outside in terms of derivatives. And then g of t is going to be left alone. Right? So here I'm going to, this time I'm just going to use black ink so that I can notate it like, oh, 1 second, I forgot my exponent. I brought the 3 down and then I subtracted 1 from the exponent. I'm squaring that whole thing. Right, as I was saying, this here, that's the g of t. Okay, and now we need to multiply by the derivative of g of t. Multiplying by the derivative of the inside, that's the chain rule. And now that is going to be itself another application of the chain rule. Holy moly, what's going on? This is a complicated function. It's actually a 3-step process. Okay? What do I mean? T goes to t squared minus 4t plus 1, and then we take sine of that, and then we cube it. So overall, there's actually 3 different pieces to the composition. We just used the chain rule once for this raising to the 3rd power, that generalized power rule, right? 3 times g of t squared times the derivative of g. I'm just writing the derivative of g in that other notation. But now to evaluate this derivative, that itself is a composition, so we need to use the chain rule again. Okay. So to evaluate this, we need to apply the chain rule again. Okay. Apply the chain rule again to evaluate the derivative of sine of t squared minus 4t plus 1. Here we go. If you like, you could just compute this derivative on your own as a separate problem, but I'm going to keep all the notation present because I don't want to forget that first term that we worked so hard to get. So in other words, I'm going to keep this first term. It's going to come along for the ride. There it is. And now we're going to take the derivative of sine of t squared minus 4t plus 1. Okay, so to take the derivative of that function, again there's going to be an inside and an outside. Let's use two different colors. All right. To take the derivative of this entire thing, we first do the polynomial. So that's going to be the inside. That's going to be in red. And then in a slightly different color of green, sine, that's the outside. For this second instance of the chain rule. Right? Those are the inside and outside functions. Oh, here, let me show you. Those are the inside and outside functions for this derivative, which we're about to evaluate. Okay, here we go. First, the derivative of the outside function. So the derivative of sine is cosine. So we're evaluating cosine at the inside function, which is t squared minus 4t plus 1. There you go. So evaluating the inside function, plugging it into the derivative of the outside, but then we need to multiply by the derivative of the inside. So what's the derivative of t squared minus 4t plus 1? It would be 2t minus 4 by the power rule. So again, this is a three-step process. We took the chain rule twice. The first time we took the chain rule, it was for the cubing function. We brought the 3 down, lowered the exponent by 1, left the inside the same, plugged in at the inside function. But then we need to take the derivative of the inside function. So we're decomposing a three-step process by taking the derivative of the outer process, then taking the derivative of those two inner processes, again using the chain rule. So we took the derivative of overall the second function, which is the outside function here, the sine function. We took its derivative, got cosine, evaluated at its inner function, and then multiplied by the derivative of the inside. And so that's the answer. That's the answer. Notice that we have a sine of something all being squared, so if we want, we could rewrite this in a slightly nicer form as sine squared of t squared minus 4t plus 1. That's being multiplied by cosine of t squared minus 4t plus 1, and then multiplied by 2t minus 4. That's the derivative.
Log lady. Right. Hi. Can I ask her about her log? Many have.
Next example, let's take the derivative of sine of e raised to the power 7x squared plus 2. Well, again, we see that we're going to have 3 different steps. There's 3 different functions being composed here. We're going to have to use the chain rule twice. Here we go. First of all, sine is the overall outer function. So we're first going to apply the chain rule using sine as the outer function. The inner function for that instance of the chain rule is going to be this entire piece, the thing that we're taking the sine of. But later on, when we take the derivative of that inside function, we'll have to use the chain rule again. 2 instances of the chain rule. Here we go. The derivative of the outer function, the derivative of sine, is cosine. But now what are we evaluating cosine at? We're evaluating it at the inside function, right? 7x squared plus 2. No derivative there. That's just is what it is. We only apply the derivative to the outer piece for that instance of the chain rule. But now we need to multiply by the derivative of the inside. So the derivative of e raised to the power 7x squared plus 2. In order to take that derivative, we need to apply the chain rule again. Let me write that down for you. We need to apply the chain rule again for that part. Don't be afraid to do that. We're going to apply the chain rule again. So in other words, we need to decompose this as a composition. 7x squared plus 2, that's going to be the inside, the innermost function, because that's the first thing that happens to x, and then you're taking the exponential of that. So the outside function is going to be the exponential function. The outside function for this instance, the chain rule, is going to be our friend, the exponential function. Okay, let's apply the chain rule again. First of all, this outer piece, everything's done here. There's no more derivatives to take, so let me write it in black ink, because it's not part of this new instance of the chain rule. We're now taking this derivative using the chain rule. So we have to first do the derivative of the outside function. That's just the exponential function. So we're raising e to the u. It is its own derivative, right? But what's u? It's just the inside function. Right? So again, we just get 7x squared plus 2 on the inside. I did take a derivative here, but remember the derivative of e to the u is e to the u. But we're not done. We need to multiply by the derivative of the inside function. And we do that using the power rule. Right? So 7x squared plus 2, we bring the 2 down from the exponent and subtract 1. So we just get 2x there for the derivative of x squared, and plus the derivative of 2. Well, the derivative of 2 is 0. It's a constant function. So that was the chain rule again. Just to remember our notations, remember we could think of this as like an f prime of g of x, where here g would be that inner function 7x squared plus 2, and this is your g prime of x. Alright, so when the dust settles, that whole thing multiplied out, that's the derivative. I don't see anything we can do to simplify. Let's just leave it as is. It's cosine of e to the 7x squared plus 2 times e to the 7x squared plus 2 times 14 of x. I guess I could move the 14 out front as a constant out front. It's too late now. Let's just leave it that way. It's still correct. Same function. I can put the 14x out, leave it here, or put it out front. It's the same function. That's the derivative.
Hello again. Can you see through a wall? Can you see through human skin? X-rays see through solid, or so-called solid, objects. There are things in life that exist, and yet our eyes cannot see them. Have you ever seen something startling that others cannot see? Why are some things kept from our vision? Is life a puzzle? I am filled with questions. Sometimes my questions are answered. In my heart, I can tell if the answer is correct.